Welcome back to our lecture Machine Learning, and in the following videos we want to talk about deep learning neural networks. So you learned already about logistic regression in the previous videos, where we defined the underlying probabilistic model in the following way. So we want to make a prediction, categorical label for a specific input X, and the idea was that this follows a Bernoulli distribution in the case of binary classification. So we have class 0 or class 1, so it's the outcome of a Bernoulli. And what was this parameter of the Bernoulli distribution? It was simply here the sigmoid of a linear function. Okay, so we had our input data X, we had our learned parameters W, multiply them, so a linear function, and then we have the sigmoid to map it to 0, 1. Okay, so what we technically get out is the probability of, for example, class 1. So this gives you the probability of that the sample X belongs to class 1. Okay. So we can also represent this graphically as you see it here on the right hand side. Okay, so we have here our input data. Every node corresponds to some input data, and we added here this constant 1, right? You know, we can use this constant 1 to absorb the bias term, so we don't have here specific bias added, but we just absorb it into the X, right? So this is what you see here. Then on the edges, we have the specific weights, right? So every input is multiplied with a specific weight, okay? And then this technically is summed up, right? Because that's the dot product that's here, this calculation, that's just the sum. And then finally, what we're doing is on this sum, on this output here, we are applying a sigmoid function. Okay, and this is what you see illustrated here in this plot. Okay, so this graphic more or less represents what we are doing in a logistic regression. Input data multiplied with the weights in a linear way. Then we apply a so-called nonlinearity, a sigmoid, right? This shape here, sigmoid, and then this is the outcome of our final model. Okay. And indeed, this is what you see here again, right? So what you should remember is that this term is the outcome before we apply this so-called nonlinearity, this activation function. And then finally what we do at the end is we apply this activation function, and then we have our prediction. Okay. So this here, and you see this later, is also the illustration which many of you might have seen already in the neural network domain. This already corresponds to some very tiny neural network as we discuss it later. Okay, so this is the graphical representation of logistic regression. And now we want to dig into more into this neural network world, and we want to see what are the problems of logistic regressions and why is deep learning so popular and so powerful as an alternative or more advanced principle. And for this, we can, for example, start with a very famous XOR data set, which looks like this here. So here we have objects from class red and objects from class gray, let's say. And what we can clearly see is that we can't linearly separate this data, right? So remember, what does linear separation mean? It means we can find a hyperplane which separates these two classes perfectly. And here you see whatever hyperplane we are picking, so in the 2D case here it's these lines, right? We cannot find a perfect classification. So this data set is not linear separable. And as you learned logistic regression, so this model here, this of course leads to a linear decision boundary. We discussed this earlier in the previous videos. So logistic regression means linear decision boundary means it can only handle linear separable data. So the logistic regression cannot classify this data set perfectly. So what can we do then? And this is some of what we already learned in linear regression settings. Of course, we can apply basis functions. We can, simply speaking, transform our data to a different space, and in this space we can try to do our work. Okay. So here's again just the setup, right? We have our input X, we have the targets Y we want to predict, and then instead of just using our old definition, let's directly look here, we have our parameters and we multiply it with X. We now operate on the transformed data. Okay, so we have here again this phi, which are the basis functions, right? So any kind of transformation you can imagine. And then we are multiplying this transformed data with our parameter vector W. Okay. So this is equivalent to what you learned already in the standard linear regression setting. And of course, what you see again is that this model here is linear in W. Right? It's still linear in W, but of course it's no longer linear in X, depending what kind of basis transformation you are using. Okay. And not surprisingly, doing this, we can handle more complex scenarios. We can handle now, for example, this XOR dataset also with a logistic regression model. And how? By picking these basis functions. So here we have a specific example. So let's say we pick this kind of basis function. So this one basis function, 5 plus first feature plus second feature. Okay. And then we have a second basis function, which is 5 minus one feature and the other feature. Okay. And if you do this, if you apply this on this data set, you will get, for example, this output. Okay, so this is a good homework for yourself, right? Take a point here, right? You see the coordinates 4 and minus 2, for example. Apply this transformation and apply this transformation. And at the end of the day, you get this base. Okay. So now you clearly see, once we have done this basis transformation, of course, we can now find a linear hyperplane which separates this data, right? Because now we could, for example, cut here, right? And then we see upper left is red and lower right is mainly gray, for example. Okay? So you see in this space, we can do a much better job. And again, you can illustrate this graphically, right? What we just did. We start again with our input data. So every circle here corresponds to the input, right? So we have x1, x2, and this bias term, right? Then we apply a basis transformation, and here it's again like a linear basis transformation, right? We take 5 times the first feature, which is here the constant 1, then 1 times x1 and 1 times x2. And this gives you the first transformation. And then again, we apply a nonlinear activation function, a sigmoid, like here, for example. Okay. And then the same, for example, here, right? We have our input. We have our second transformation. Sorry, we have the input 5 times minus 1 and minus 1. Okay. So similar to before, you see that on the edges here, we have the corresponding weights, right? Going back here, we had here the weights on the edges, which are multiplied with the incoming signal, with the x's. Okay. And now it's exactly the same, right? So we have here the input, and this is multiplied in a specific way, right? So by the way, this space here is already shown after the sigmoid transformation. Right? Just be careful here, because the space is between 0 and 1. This is showing you the space after we have applied the sigmoid transformation, of course. So this is what is illustrated here. Not just the basis transformation, but the basis and the nonlinearity. Okay. So then you see what we're collecting here is as before the output, so to say, right? We have the input, we have the nonlinearity, and we have here the output. And now again, we have 2 features, right? 2 transformed features, this feature 1 and this feature 2, right? Which corresponds to, so to say, this here corresponds to this part, and this here corresponds to this part, right? And we can now apply logistic regression on these 2 features. Meaning we have again our 2 weights, W0 and W1, right? They get multiplied. We have again another nonlinearity, another sigmoid, and this is our output. Okay. So you see, we can put this basis transformation into the same illustration as we have seen before, right? It nicely fits to this framework. And then you see that we get this overall pipeline, so to say. How can we handle our XOR data set? We can handle it by having specific custom basis functions, basis transformations. Here, one more time, you see it in a more compact way. Input data, the weights corresponding to the basis function, right? So this is how we transform our data. We have the first activation function, nonlinearity, the sigmoid function. Remember, this is usually applied element-wise, right? And then we have again some weights, the weights of the logistic regression. And we have again our final sigmoid layer, which maps it between 0 and 1, which indicates a probability of being in class 1. So this is just the full model we are using, which includes the basis transformation as well as this classification step of the logistic regression, all in a single function. Okay. And this, as I said, can now handle this XOR dataset in a much better way. It can handle also nonlinear separable data, right? This classification function. And how can we now train this? How can we find this this model? And as usual, right, we have here some unknowns W. And of course, we can learn these by, for example, minimizing some specific loss function. And indeed, as before, what we have seen for logistic regression, we can use the same loss function, right? Because at the end of the day, what we are predicting here is, again, the probability that this instance X belongs to class 1. And then we have the other probability that belongs to class 0 in a binary classification setting. And then the usual loss function we should use here is the binary cross entropy, because this corresponds to maximizing the likelihood if we assume this Bernoulli model from a probabilistic point of view. Okay? And indeed, this is what we can do now as well, of course, right? So how to find the parameter W is by optimizing the binary cross entropy loss, right? Which you see again, what was it? It was the true label, the ground truth, and then our prediction, right? And the prediction is now just a more complicated function. But at the end of the day, we can again just optimize, for example, with gradient descent over the parameter W to find the optimal weights. Okay. So now essentially we just train on a more complicated model where the basis transformation is included in our function. Okay. So now, of course, the natural question is, how can we find this basis function? Here well, by some magic trick, we found it's 5 plus x1 plus x2 and 5 minus x1 minus x2. But how can we do this in general, right? Of course, we don't usually know how it has to look like. And of course, different data sets might require different basis functions, okay? And this is now the core idea, that we not only want to learn the linear logistic regression parameters, so the parameters which we use, so to say, in the last step, but we can also now at the same time learn the parameters of the basis transformation, right? You see, before we had these kind of parameters of our basis transformation, right? 5 plus 1 times feature 1, 1 times feature 2. But of course, we can say that these are also parameters, right? We don't want to pick them by hand, but we want to learn these parameters. And this then more or less brings you to the full idea of neural networks already. We want to learn, so to say, the representation of our data, or the basis transformation. How can we transform our data and the weights, for example, of this logistic regression model at the same time. So if you look now at this function we had before, we now just have a larger set of parameters. We have here the parameters we have seen before already, right, for our logistic regression setting, but now also the parameters of the basis functions are unknown. They are not given anymore. Well, if you look at this illustration again to make it clear, right here we have the raw input data. Then we have the weights, how this input data is transformed in the first step, right? I remember again here you see this notation, how it's used, so to say. So this first indicates the weights of this first part, right? You see here the first index is 0, here the first index is 1, right? Because this is a 0 level and the first level, right? Then you see here the second coefficient corresponds to which input we are looking at. So here it's the 0 input. So this is 0's input. This is why you have here 0 and here 0. This is the first input. This is why you have here 1 and here 1, right? And then the last index corresponds to which output this is going. So to say, right, so here's a 0 because it goes to the 0's output. Here's a 0 because it goes to the 0's output. Here it's a 1 because it goes to the first output, right? We start counting at 0. So you see by these three coefficients, we have, so to say, have a specific index for the corresponding weight, right? It's the layer, the level, then it's the input, 1, 2, 3 in this case, or 0, 1, 2, and then it's the output where this is going to, which is again 0 or 1. And you see the same here, right? First layer, first, so 0's input, and we have only one output anyways. Okay? So you see now you get a bunch of more parameters, which we can all collect usually in a big parameter set or multiple parameter matrices, which we often call just W. Okay? And this is now our parametric function. So this is a function which has a couple of parameters which we don't know what they are. But of course, we can now do the same as before. We can write down our loss function, the binary cross entropy. And again, here you see our prediction model, which just have now more parameters. And now we train all these parameters at the same time. So when minimizing, we optimize over all these parameters. So from an intuitive point of view, again, what we are doing is we are learning the transformations, this part, or the often called representations of our input. This output is, so this representation, this 2D representation is often called like a representation in neural networks. This is often why it's called also representational learning. And we are learning the classification model at the same time. So the weights of the logistic regression and the weights of our representation are learned at the same time. And this is often also called an end-to-end learning. Okay, we don't do a priori some feature transformation, then we learn the classification, but we do this jointly end-to-end from the raw data to the classification task in one big pipeline end-to-end. Okay? So this is what we are doing, and this is the core of neural networks, so to say, that we have this end-to-end learning where we learn this feature representation simultaneously with the actual classification model, for example. So what you see here is indeed already one of the most famous neural network architectures. It's called a feed-forward neural network and with a so-called one hidden layer. Okay, so this layer here in the middle is called a hidden layer because it's neither the input nor the final output. It's in the middle, so to say. It's not observed. It's a hidden layer. Okay, it's a feed-forward neural network, or often also called a multi-layer perceptron. Okay, so here we just have one input, one hidden, and one output layer in this multi-layer perceptron. Okay. So what is also important to note in this neural network world, we have lots of flexibility. So these operations, which I'm indicating here, these are called, as I said a couple of times already, activation functions or nonlinearities. And in principle, you can freely choose them, right? So here, this is like the basis transformation, right? So the first feature extraction, you don't have to use here sigma. You can use any other kind of function which you think makes sense. Here for the output, we see this later. Of course, you should adhere to some specific choices. So if you, for example, have a binary classification setting, you might want to use a sigma here because it maps it between 0 and 1, right? And it indicates a probability that the instance belongs to class 1. But in principle, these functions can be arbitrary activation functions. And then this indeed brings us to the, let's say, most general form we can look at in this neural network world. Here you see it. Of course, we are not restricted to a single hidden layer, but in general, we can have arbitrary many deep, so to say, networks which have multiple layers. Okay, so again, we have the input layer, the input data, including this constant 1 or not, right? This is doesn't really matter, right? You can imagine that we have always this constant 1 added. We have here our first hidden layer, second hidden layer, and then the output layer. And again, what is important to remember is the following. This is sometimes not correctly illustrated in the web, for example. So these nodes here, they correspond in this case to the input data, or in this case to the hidden representations. And the weights we are learning, they more or less map to the edges, right? Every edge corresponds to a specific weight, right? One more time, we have this input and we multiply it with a specific weight and we sum it up with the other inputs multiplied with a specific weight, and then we are getting this output after applying the nonlinearity. Okay, so the weights are on the edges, so to say, right? The weights are on the edges in the different layers, and then here this is the input and the different representations, and finally the output. Okay, and then again, of course, you can stack it in arbitrary complex ways. Here we have shown it for a simple example. One more time, input, some first linear transformation, and then a so-called nonlinearity activation function. Then again, some linear transformation and some activation function. Linear transformation and the final activation functions. Okay? And as I said before, all these weights we are usually collecting into one big W, and then when we train this neural network, all these weights are learned at the same time. So we have all these different transformations learned at the same time. Okay? And here you see already what I said. This architecture I've shown you here, it's called a multi-layer perceptron, a fully connected feed-forward neural network. Fully connected means, and you see it in this illustration, that every input is connected to every next layer's output, so to say. Okay, so we have here a fully connected graph, so to say. 3 times 4 connections. And you see it here also between these two, right? Every of these 4 inputs now is connected to every of these 4 outputs. And also in the last layer, every of these 4 inputs is connected to every of the 3 outputs. Okay, so this is why it's called a fully connected neural network. Okay, and feed forward, and this is what we don't discuss here in detail. Feed forward is because the processing goes from the input only to the output, and that's it. Right, from here to here, it's just pushing forward, so to say, the information through this network, this neural network. And there are other architectures which we don't cover in detail, but they are, for example, recurrent neural networks. Okay, so again, this is essentially more or less the basic, or at least the fundamental you should know about neural networks. And simply, in simple terms, it's a rather complicated function because of this multiple levels of transformations, which is parametric, which has these W parameters. But at the end of the day, we can train these parameters again using, for example, gradient descent, as you have learned it already. And then we have found the optimal parameters, which we then can use, for example, for prediction. Okay, so I talked about these activation functions already a couple of times. So here are just some examples which are quite common. So the sigmoid you have already seen. So it maps the arbitrary input always between 0 and 1, right? It has this S shape. But there are also many other activation functions, specifically ReLU or the ELU. These are also often used. Specifically, ReLU networks are quite famous in many architectures. But again, in principle, this is more like plug and play. You can play around with different activation functions and you can see how your model behaves based on the tricks or the principles you have learned, right? Please use like a validation set to see, for example, which activation functions work. Okay. And one last remark here, again, most activation functions actually operate element-wise. So again, let me scroll back to make this clear. So here, for example, if we are applying this linear operation, right? So the output of this here is 2-dimensional, right? So here it's a 3-dimensional input and then it's multiplied with a 2 times 3 matrix. So the output of this is 2-dimensional. And then this activation function is usually operating element-wise, right? It applies it to the first dimension and then applies the function to the second dimension. This is why you see here usually only the element-wise operation, right? Where you get a scalar in, so to say. One notable exception is the softmax, which we already have seen in the previous videos, right? The softmax is coupling together all these inputs, right? You get a vector in, and then the output is like a normalized vector, so to say, right? So the softmax is not operating element-wise. The rest usually is operating element-wise. And if you're playing around with these modern deep learning frameworks, you can see that you can really pick different activation functions. As I said, you can just play around. You can specify how many layers you want, what kind of layers. There are specific layers we will talk about later in more detail. But for example, also here in the simple setting, you can, for example, say you want to have a multi-layer perceptron with 5 layers, fully connected, these activation functions, and so on and so forth. Okay. So talking about these activation functions, there's one important aspect to let's say, remember. Why should we pick these, let's say, rather complicated activation functions, or let's say nonlinear activation functions, right? You see that these are all nonlinear functions. So why don't we just pick also linear activation functions, right? You can imagine like having like here a linear line as some activation function, right? And which more or less means we don't use any activation functions, right? Because as we have seen, we have our input, then we multiply it with some weights, and then again, a linear transformation, of course, doesn't make it different. And indeed, that's the full point. If we would use linear activation functions, or no activation functions, then what will happen is the following, right? You see that we have our x multiplied with W0, W1, up to WL in these different layers. And this can all be collapsed. Right? Because if you have like 2 matrices, you can just multiply these matrices again, and you get another matrix, meaning you're still in the space of linear functions, meaning all these weights can be collapsed to a single matrix, and what you end up with is then again a linear transformation. Meaning the nonlinearities, this sigmoid, ReLUs, and so on and so forth, they are core of this neural network power. If you don't use these nonlinearities, it will all be reduced again to a linear model, meaning at the end of the day, it would be again just a linear transformation, which doesn't help you at all in, for example, classifying complicated data. Okay, so these here are indeed core to get a powerful model, right? Because if you get rid of them, it all collapses and there's no benefit. So nonlinearities are core. Okay, and again, of course, then I guess it's clear if we use nonlinear layers, right? If we have here these activation functions, of course, in general, we can't collapse, right? There might be specific settings where we can collapse it, but in general, of course, it's not possible to do this. Okay, so let's talk about a bit more the power of these neural networks now in a bit more detail. So I said the nonlinearities are core, right? Without the nonlinearities, it all collapses. But how powerful are we if we use these nonlinearities? And indeed, the answer is we are universal in some sense. Universal meaning that we can represent any function under some specific conditions. So technically, it means any continuous function over a closed and bounded subset of your domain, for example, RD, right? So any of these functions, and these are usually functions you might want to care about, right? Any of these continuous functions can be represented by a multi-layer perceptron if we use specific activation functions, so-called squashing activation functions, which, for example, includes the sigmoid, and if we use only one hidden layer, okay? So we have the input, one hidden layer, the output then, right? Any function, any continuous function, simply speaking, can be represented by a multi-layer perceptron. With the catch that if we use enough hidden units, okay? So if you look back, essentially, do this this model here, right? This model, is enough to represent any continuous function, given that this middle representation is large enough, and given that we, for example, use a sigmoid function. Okay? So we take our input, we map it, and then we put it back. This, I guess, intuitively is also not too surprising, right? If you really think about that, this here is doing some kind of feature extraction, and if you make this arbitrarily large, you can extract, so to say, many different features, right? And then if you have extracted enough features, it might not be surprising that we can, at the end of the day, just represent any complex function, right? So we don't dig here into the details, but in principle, what you can remember is that with a neural network, we can represent any function if the neural network is big enough. And this is indeed, this is on one hand the good news, right? But on the other hand, it's also bad news because it can on one hand be very large. And on the other hand, we don't know how large it has to be and how to find this then in a constructive way, so to say. Okay, and by the way, this also holds for discrete data, not only for continuous data, but with the same problem. The network might be very huge, and we don't know how huge it has to be to represent this function, and we are looking at in a good way. But in principle, you see that neural networks are universal. They are arbitrarily powerful, so to say. And indeed, this expressiveness and this basic idea of neural networks you can also see in a specific demonstration. So here's a link, and in a separate video I will talk about this in a bit more detail. But here in this demonstration you can play around with this basic idea of neural networks. You see here in this video, this screenshot of the videos of this demo, like the input, you have then different layers. Here in this case you have 3 hidden layers, for example, with a specific number of neurons. You can pick specific activation functions, and then you can try to classify specific data sets. So as said, in another video I will explain this in more detail, but there you can again see how all these plug and play, this Lego kind of way of neural networks work. You can really just combine these different kind of layers and activations, and then you can handle very complicated settings. Okay, so here just quickly a few more words on this expressiveness. I already said this, that we can represent any function with a single hidden layer. However, with the catch that it has to be very or potentially very large. And indeed, this is also one theoretical reason, at least, why we want to add more layers, right? So usually we don't stick to one layer, which is very wide. It's often called a wide network, where we have many neurons in one layer. But often we are going for deep networks, right, we have many layers which are not as wide. Okay. And indeed, you can show this also theoretically for some functions which we want to represent, right? Well, let's say for some classification functions, if we use only a few layers, we might need a very wide network, meaning many parameters as well, right? Because as we have seen, right, a wide network means we have many parameters, right? Because we have all these connections. In contrast, for these functions, if we use a deep network with more layers, we only need a few parameters, meaning only a very narrow, so to say, network. Okay, so few layers could mean many parameters, while more layers sometimes leads to fewer parameters. Okay, and indeed, this is also often what you then see from a practical point of view. So deep networks with a couple of more tricks, right? So networks where we have many layers, often easier to train. They often generalize better. They are meaning faster to train. They sometimes have fewer parameters, right? And this is all beneficial also from a practical point of view, okay? So this is also the reason why in practice architectures are not usually extremely wide, right? So they're not extremely wide in this sense, but they are rather deep. Okay, you see it here. Again, input, multiple levels, multiple layers until we reach the output. And then here in the middle, we have these not extremely wide network, so to say. I mean, it's still rather wide compared to, let's say, a logistic regression where we directly go to the output, but it's not like billions of neurons, for example. So here it's again written what I more or less just said. So there are specific families of functions where reducing the network by one layer, so removing one layer leads to an explosion of the parameters, so to say, right? That we need exponentially many units when going in the network with k-1 layers, for example. Indeed, you can construct such scenarios. And then just on a more informal level, how you can interpret these kind of layers, I said it already a couple of times, you can interpret it as some kind of representation you have extracted, you have learned from your data. So you start with the raw data, and then in the first layer you have extracted some, intuitively speaking, low-level features which describe your data, and then the higher you go in your hierarchy, the more high level are these representations, these features. At least this is the hope, what the vision of neural networks are, that these different layers represent different kind of semantic concepts. There is a bit of an issue still from a research point of view, and you can see some counter examples to this, adversarial examples, for example, which are covered in our advanced lectures. But intuitively speaking, you can think about that these different levels extract different features, which at the end of the day help you to do the actual task, whatever this task is. Okay, so this was the first very quick introduction to neural networks. So I guess you already got a good idea. What you should really remember is, in principle, a neural network is just some very complicated function which is composed by doing these different layers. And every layer is like a linear transformation followed by a nonlinear activation function. And then again, this is just simply stacked to get this very complicated function. And at the end of the day, we can train it, for example, via some loss function, and we train all these parameters at the same time. We do some end-to-end training of this full complex functions from the raw data to the actual target. Okay, and of course, this is not now restricted to binary classification. So far we just talked about the simple setting where the output is like a scalar which represents the probability of class 1. So we had the sigmoid in the last layer. But of course, this is not what we can just do with a neural network. Neural networks in general are very flexible. And indeed, if we want to use neural networks not only for binary classification, the only change we technically have to do is we have to change the activation function in the final layer, in the last layer. So the layer before, which gives us the final output, so to say, and the loss function, how we want to train it. Because you know the loss functions often corresponds to the actual probabilistic model we are looking at, like binary cross entropy corresponds to our Bernoulli model. And indeed, this is what you see here in a short summary. So far we talked about a binary classification, so 0-1 classification. So technically, from a probabilistic point of view, this corresponds to having a Bernoulli variable for our y's, right? Y can be 0 or 1, so it's a Bernoulli variable. Then what we can use or should use for the final layer, for the last activation function, is the sigmoid, because it maps it between 0 and 1, which you can represent or interpret as the probability that this label is 1. Right, so the sigmoid makes sense. And then what we have seen before in the other videos is that the loss function you should pick in the best case or in some default way is, for example, binary cross entropy, right? Because we know that this corresponds to the maximum likelihood estimate. And then, not surprisingly, this is also what you have already seen. We can have like discrete, so multiple labels, for example, classification. So we have a categorical distribution for our y's class 1 up to class k. What you know, and this is what we have already learned, is you should not use a sigmoid, but a softmax. Right? The last activation function of your neural network should be a softmax, because this gives you a probability vector, right? Sums up to 1, which you can represent as a probability for all these k classes. And what you also know already is that we can then use cross entropy as a loss. And finally, if you, for example, have a continuous output, meaning you want to do, for example, regression, right, with a continuous output, you can, for example, assume that your target follows a Gaussian. So this is what we assumed in linear regression, right? The noise we have, or the target we are predicting, follows a Gaussian distribution, right? This is the variation we are allowing in our target. Then what you know is that the loss function should be, for example, the squared loss, right? This corresponds to the Gaussian here. And then what you can do in a neural network is, in the last layer, you don't use any activation, right? Because you want to have an arbitrary domain, for example. You can just use an identity, technically speaking, so no activation. Okay. So you see, by changing the loss and changing the final layer, you get different settings. And here is what I more or less just said already in this short table, just for your reference. And I just do it for one example here. So if your data is like binary classification, meaning the target is 0, 1, then you want to use this model here. Okay, so we have our complicated function corresponding to multiple layers. And in the last layer, we use this kind of activation function, the sigmoid. So here this A corresponds to the output before we apply the last layer, right? Output of last layer before the activation. So the pre-final output, right? The pre-final output before we apply this sigmoid, and this is often called in this classification setting the so-called logits. Okay, so A are the logits, and then once we apply the sigmoid, we get our final probabilities. Okay, so A indicates here the logits. And here you see what I just said, right? So this would be your last activation function. What you do in the middle doesn't matter, right? So this A is the output of some multiple transformation. What you do in the middle can be anything. It can be sigmoid, but it can be also many, many other operations, right? It doesn't matter. Only the last activation function matters for the task at hand, right? Because here it's a Bernoulli then, and then we have the binary cross entropy, where you again see what we have already discussed before. Okay. Here the example with multiclass, right? Y is a one-hot vector. Again, A is now not a single scalar output, but multiple. It's a vector of logits, right? Say k many, and then we have the softmax in the last layer, and we have our categorical general cross entropy. And finally, right, if we have like a regression setting, so the target is continuous, we just use, for example, the logits, so to say, as an output. We don't need any activation function, because this can already be some arbitrary number. Okay. And if we want to have a Gaussian as our probabilistic setting, we know that this corresponds to our squared loss formulation, right? So ground truth, predicted value, squared, and summed up over all training samples. And indeed, this is, again, the full power of neural networks. Not only can you plug and play with the actual different kind of transformations, right? You have these different layers where you can play around what you want to do, but also by just changing the loss function and changing the last layer's activation, or using no activation, or using softmax activation, you can apply it to many, many different tasks. But the underlying principle stays the same. And that's a big advantage. It's a very general and flexible model which can handle multiple different machine learning tasks. Okay, and then finally, of course, we are not restricted to these supervised learning settings, which we have seen so far only in this lecture, regression or classification, but we can also use it for unsupervised learning, which we cover later in more detail also in this course. We can use it, for example, in an architecture known as an autoencoder. Okay, we'll cover this later in our lecture, which can be used as dimensionality reduction or compression, for example. But there are many, many other unsupervised neural network approaches like a variational autoencoder, generative adversarial networks, GANs, some of you might have heard about this, or in general unsupervised representation learning, for example, representations for text or representation for graphs and so on and so forth. So for all these domains, we can also use neural networks. Unfortunately, we don't have time to cover all this in the intro course, so all these last topics will be covered in our advanced lectures, but we will cover briefly the autoencoders in one of the later videos. But you see, again, here also neural networks play a role. They are very powerful and indeed they're also very successful in all these different applications. Okay, one last point. You see, again, plug and play, Lego. We can choose the different activations, we can choose the different layers, we can choose the last layer's activation specifically, and of course what I said is we can choose a loss, and here just like a summary slide, right? We have already seen that we can use a cross entropy or the mean squared error. Of course there are many other losses, okay? So we are not restricted to these. So the ones we have talked about so far, they have some nice interpretation from a probabilistic point of view, and also some others have, but in principle you can choose any loss you feel which makes sense, with one important point. And this is what we talk about later also in more detail. The loss should be, in some sense suited that you can do gradient-based training, because gradient-based training is usually what you're doing in these neural network approaches, in these neural network frameworks. So you should have losses which are suitable for example, having a nice gradient. And this is also why, for example, the 0,1 loss we have seen at the very beginning is not very suited, right? Because we had this step function here. So doing gradient-based training on this is not a good idea, right? Because the gradient is either undefined or often just zero, so we can't do gradient-based training. So beside this point that the loss should allow you to do gradient-based training, you are free. You are free to choose this loss as well, right? And we have seen these two as said, but there are many others. So mean absolute error, for example. So here, this is specifically useful if you have outliers. And this mean absolute error is also not the best, let's say, the easiest to use if we do gradient-based training, because the gradient is independent of the distance from the optimum, because it looks like this here, right? The gradient is always 1, right? It's like this function. So the gradient is always 1 or minus 1. So it's not the nicest and most informative gradient, but it's indeed nowadays with the new optimizers possible to handle this, okay? And again, this is often helpful for if your data, for example, has outliers in a regression setting, for example. But there are many others, like the Huber loss, which is also very famous from a robust statistic point of view. We have the Wasserstein loss, for example, which we can use to compare different distributions or Kullback-Leibniz divergence. So if your output is a distribution, or like you want to compare sets of vectors, for example. So for different kind of outputs you're interested in, you have different loss functions, and you have different loss functions have different properties, but in principle you can see which of these loss function applies to your scenarios. Okay, so this was a high-level idea showing you the flexibility. In the next video we want to dig a bit more detail on the parameter learning, and you will see that parameter learning has to be done carefully in neural networks to make this all work. But let's first take a short break, and we see us in a couple of more minutes. Bye bye.